Okay, so every time you are saying continuous and intermittent gas lift. So continuous gas lift normally will be used when productivity index is more than 0.5 barrel per day per psi. Productivity index up to 0.2 also can be possible, but in that case normally people will be using intermittent gas lift when productivity less than 0.5. Continuous gas lift change to intermittent gas lift after further dropping of reservoir pressure. Reservoir pressure when dropping, actually Pi will be dropping, so that time you can change to intermittent gas lift system. So an intermittent gas lift system also will give lower production rate. The reason is that you have one intermittent gas lift system, actually you allow gas to build up, then you inject gas, allow liquid to build up. Okay, let's say a small amount of liquid is coming, so you allow say 1 hour, 2 hours, 3 hours, liquid column will be building up, so production rate will be almost stopping, then you inject gas. When you are injecting gas, whole liquid slug will be lifted up and you clean the whole wellbore actually. So again the fluid will be entering into wellbore, again column will be built up, again inject gas from annular area, again remove the slug. So that way intermittently you will be doing this one. So that's why productivity is lower, but in continuous gas lift system normally productivity will be higher. The potential of gas lift wells controlled by gas injection rate or GLR. Significant gas injections are low injection rate. Yeah, when injection rate is very low, so normally the production rate will be lower definitely. Minimum volume gas for maximum efficiency. Sometimes you try to think the maximum efficiency of the whole system, so in that case you try to inject minimum volume gas, but optimal volume will be like maximum liquid production rate we are getting, so that is will be optimal production rate. Excessive gas, if you are giving excessive gas, actually production rate will not increase, it will decrease further, because some gas will create maybe annular flow or mist flow, so that will not give higher efficiency, rather it will reduce the efficiency. So when you are installing a continuous flow gas lift system, there is some formula you can use. PWH wellhead gas pressure plus G, this is GFA, actually they have whatever notation they have used, I am using the same notation, GFA L plus GTB, this is GTB D minus L equals PWF. Here D is the depth and L is the injection length from surface. Okay, from surface how where the point of injection is happening. So this is D minus L, this part, and this is normally this point of balance and point of injection, normally they will be keeping 100 psi approximately, thumb rule will be 100 psi, difference will be there. So they are putting 100 psi here. Okay, so point of injection, point of balance, and this is PR, this is PWF. Okay, and this is tubing pressure PT. This is tubing head pressure and wellhead pressure is different actually. Tubing head pressure, wellhead pressure means you are adding some more pressure. Okay, if you have more wellhead pressure, actually flowing, your flow rate can go down, because let us say 100 bar pressure already there and you are adding 5 bar more. So actually your PWF increasing, PWF increasing means PWF PR, reservoir pressure minus flowing pressure difference is going down, so your flow production rate can go down. So as low as possible in wellhead you can maintain, so that you can get more production. And so tubing head pressure means you are not adding the wellhead pressure actually. And casing pressure PSO, surface pressure, surface operating pressure, sometimes they say PC also, like casing pressure. This is PWH, wellhead pressure, GFA is the gradient, average flowing gradient, average flowing average flowing gradient above the point of injection, above the point of injection. Okay, this is the above the point of injection, this part. Okay, so this gradient, and GTB actually below the point of injection. Okay, GTB below the point of injection, BLOW, below the point of injection, that gradient, and D is the total wellbore depth, L is the point of injection from surface length, PW is the flowing pressure. So this is the basic formula for continuous flow gas lift system. Location of valves actually. So normally gas lift system will have several valves. So one top valve will be used for unloading purpose only, and normally this will not be operating valve. Again, the bottommost valve cannot be every time, it may not be the operating valve. So bottommost valve many time it will be operating valve, but it may not be true that all time it will be. Okay, if a well is loading with 0.5 psi per feet kill fluid all the way to the surface and 800 psi available to the unloading with, then the top valve may be placed at 1600 feet, neglecting the column weight and assuming zero wellhead pressure. Okay, if well bore is here and gradient is 0.5, then actually first valve can be placed at 1600 from the top. But if you have wellhead pressure also, you have to add that one. If you have friction, then again you have to add that one. Otherwise normally it can be 1600, neglecting the gas column weight. So here they neglected the gas column weight. Gas column is gas is having its own density, because of that some weight also will be coming up. If valves are placed in a well with fluid level 3000 feet, top valve can be placed at 3000 feet or slightly lower. So nearby, see here. Injection gas rate, how much gas you can inject. So here there is formula QSG QGS. Okay, they are writing like this: TGLR minus GLRF QL. Okay, so QGS volume of gas injection rate, SCF, standard cubic feet per barrel. TGLR, total gas liquid ratio at the point of injection, standard cubic per barrel. GLFR, formation gas volume gas liquid ratio. This is the temperature correction factor. If temperature is changing from surface to the injection point, then temperature correction factor can be written as 0.0544 square root of gamma g TVD. So gamma g, gas specific gravity, TVD is the temperature at valve depth in Rankine temperature. Here you have to remember this Rankine. Okay, corrected volumetric gas injection rate equals QVD, it becomes VD, it was only S, now QSG into TCF. So this will be the gas injection rate. Okay, so you should remember the formula. So I can give some problem based on these formulas. Okay, types of gas lift installations. Normally there will be three types. One will be open installation, semi-closed and closed installation. So what is open installation? Open installation, you can see this tubing left side is not having any packer. There is no packer. Okay, so this is open installation. Okay, and if you see the second one, you have packer actually. Tubing is there and tubing is connected to packer. This is casing, and open installation, casing and tubing. Tubing is hanging only, so there is no fixing with casing or no packer. But in semi-open case, this was semi-closed. Semi-closed case, you have one packer. So and in closed case actually you have packer plus you have one valve also. Okay, so that backflow, reverse flow not possible to the reservoir. But in open flow, open system, open type of installation, if you are injecting very high amount of gas, that can go back to your reservoir also. So continuous flow application is possible for open and semi-open. Continuous flow, okay, but it is intermittent. For intermittent, it can be semi-closed or closed applications. Okay. because in intermittent case you need very high amount of gas quickly. So, you need to close all this with packer plus valve also. But in continuous flow actually you are injecting certain small amount of gas continuously. So, open also can be okay for production rate, to enhance production rate. Okay, so in unloading process, so basic part of the gas lift system when you are operating the system, so first you have to unload. So, what happens initially you drill a hole and you kill the wellbore before you start producing. Okay. So, when it is killed means high density fluid is there inside wellbore. High density fluid, how it will be like this, you have casing and you have tubing. Let us say I am assuming this there is one packer also there. Okay. And whole area will be filled by same liquid because we have gas lift valve. Okay. Let us say 1, 2, 3, 4 and all the valves will be open initially. All the valves will be open. So, in that case what happen? So, because of valve is open, so all the kill fluid or high density fluid will be filling all this area. So, there will be no productivity because density is very high. So, reservoir pressure and the kill fluid total hydrostatic pressure will be balanced, so that no fluid will be coming in or going out. Now, when you are unloading gas, unloading a wellbore, so you have to actually you are removing this kill fluid. How you are removing? So, gradually you inject gas from surface and remove this casing area fluid because this you are injecting from annular area. Okay. So, this from this area we are injecting liquid. So, gradually you remove this annular area fluid. How you are removing? You inject very high pressure gas and gas will be entering through this valve. Okay. And liquid will be going out. Okay. So, this time when you are first time injecting gas, so gas is not entering into your tubing, rather liquid whatever there inside your annular area that will be entering into wellbore and it is going out. Okay. And to resemble this one, they have made one concept like U-tube type concept. What is like this? You can see one system is like this. Okay. I can assume this is tubing and this is annular area. This is annular area. Okay, this is tubing area. So, you inject gas from here, casing. Okay, casing pressure will be there. So, you are injecting gas. Because of gas, you are displacing this liquid by your gas only. Okay. So, here also same thing happening. If you see this right side drawing, gas replacing the liquid. Okay. And so, true vertical depth TVD, normally we say true vertical depth. So, many time in oil and gas industry we use the term measured depth and true vertical depth. True vertical depth means actual depth. Measured depth means like for example, this is a wellbore. So, in that case total measured depth will be total length, but vertical depth means this one. Okay. So, measured depth will be higher than vertical depth. Flowing pressure PWF is here and completion fluid pressure rho F, completion fluid or kill fluid. This is kill fluid actually, or completion fluid. Kill fluid means high density fluid. So, kill fluid you have to replace. So, you are from surface you are giving very high pressure, so that the kill fluid will be going out of the wellbore. Okay. P wellhead pressure, PSO or injection pressure on the surface. So, the formula becomes PSO equals PWH plus 0.052 rho F minus rho G into DG. DG means gas. Yeah, the gas column depth. Okay. PSO. Okay. This is the formula for calculating PSO, how much pressure you are giving. Okay. If your rho F is high, then in that case PSO also will be high, or injection pressure, gas injection from surface will be also high. Now, how unloading is happening? This is given in the book of NPTEL. So, here let us say initially assume whole wellbore, this is tubing, okay, this is casing, and whole thing is filled with your completion fluid, okay, whole thing is filled with completion fluid. So, your hydrostatic column gradient will be like this, okay, and this is depth D, and there are 3 valves they assume V1, V2, V3. Okay. So, initially whole thing is filled with liquid, completion fluid liquid, very high amount of high density is there. Now, what you do, you start injecting from the surface. When you are injecting, actually you are injecting PSO, your compressor working and you are injecting gas. So, high pressure injection happening, okay. So, gradually injecting, then you reach up to this one, okay, valve 1. So, when valve 1 is injected, so your bubbling will be started, okay. When bubbling started, your flowing pressure will be changed. So, initially we are assuming there is no flowing pressure, there is no production, okay. Now, you can see flowing pressure is there. So, you got some drawdown, okay. Because of this drawdown, your productivity started and bubbling created and you got some production, okay. Now, from there again you inject further, you activate second valve. So, when you are activating valve 2, valve 1 is closed. Initially all valve will be open, then when valve 1 injected gas, then it is going to valve 2, valve 1 will be closed. Then when it is going to valve 3, again valve 2 will be closed, and valve 3 in this case is operating valve. It, okay, again I already told that valve 3 or lowermost valve may not be the operating valve, but in this case we are showing this one as operating valve, and whole column, you see this last picture, become green. Green means actually it's a multi-phase flow created, bubbles, lots of bubbles created, okay, and hydrostatic pressure of the whole column reduced and you are getting more production. So, your flowing pressure PWF is reduced and drawdown increases, okay, and this is your reservoir pressure. Reservoir pressure you are not changing anyway, you cannot change. Yeah, here one thing, sometime people will be injecting steam or water flooding. So, those methods are to modify your reservoir, not wellbore. In our case, in artificial lift system, I am not trying to modify reservoir pressure I am not changing, okay. I am assuming reservoir pressure is fixed, but if you go to tertiary or enhanced oil recovery system, there people will be injecting gas or liquid to modify reservoir pressure or reservoir fluid properties, okay. In that case they are not changing wellbore. In my case I am changing the wellbore properties, wellbore fluid property, I am changing the flowing pressure, okay, using artificial lifting technique. But enhanced oil recovery system, they will not be changing the wellbore system, rather they will be changing the reservoir. So, both systems are different, okay. So, you can see this you start injecting, first valve got gas, it created lots of bubbles, hydrostatic pressure reduced. Hydrostatic pressure reduced means little bit flowing pressure PWF reduced. When PWF is reduced, reservoir pressure something is there, PWF reduced means some differences created, drawdown created, some extra fluid will be entering. But from surface you are injecting gas continuously, it reached to second valve, first valve closed now, second valve getting lots of gas, again further whole column weight got reduced, okay. Then you got more drawdown, more fluid will be entering, then slowly you are getting lower hydrostatic column and more fluid entering, you are getting more production, okay. And if you want to get more production, let us say someone becoming too optimistic, increase more fluid, very high flow rate of gas. So, in that case it may not get optimal production, rather your production rate can reduce actually. So, you must have the optimal production rate, optimal depth of valve, then you will get production. If you pump you try to get too much production, that will not give actually production, because it will create annular flow, bubble flow, mist flow or some other type of flow. So, that will destroy whole system actually. Okay, here is the formula to calculate valve locations actually. The D means depth valve location. If you see P wellhead, rho m actually mixture density, G gravitational constant, dV valve 1 location, rho f fluid density, G okay, valve 2 location, PKO, this is actually kick off pressure location, kick off pressure, or sometimes we say PSO also, sometimes same. Okay. So, using this formula and other formula, actually you can get different valve locations. Okay. Whenever you are talking about your gas lift compression system, so there are two options you have: reciprocating compressors, centrifugal compressors. Normally centrifugal compressor pressure ratio will be lower, I mean it can compress very low amount. So, if you want to compress very high amount of gas, high compression ratio, not amount. So, in that case reciprocating compressor is better, but both can be used simultaneously or in series one by one, because centrifugal pump or compressor can handle large volume of air. So, you get large volume of air, compress it. So, in several stages actually you have to compress. Again, when you are compressing, you have to create multiple stages also. In this later I will discuss in details how the compressors are working. So, reciprocating compressor will be like this, like one piston, like sucker pump we have seen already, valve arrangement, how this fluid is pumping, getting pumped. So, reciprocating compressor will have valve like this, okay, and piston will be there. This is piston, okay, simple as sucker pump. Sucker pump you have traveling valve, standing valve. Here traveling valve, standing, the terminology are different. Here one valve will be there opening in one direction, another will be opening in another direction. So, V1, V2, and when piston is moving forward, backward, let us say piston moving this one. So, this direction, this will be closed, the V2 will be closed, V1 will be opened, and when piston moving opposite direction, just opposite valve operation will be there. So, continuously you will be delivering fluid, high pressure gas to your system. Again, in one go or in one compression system will not work. You need to get multiple piston cylinder arrangement so that you can get proper compression. For example, initially you get very high volume of gas, compress it, you get lower volume, then compress it, then you get another volume, and in between also when you are compressing gas, because of this Charles law, PV equals RT, you can remember PV equals RT. When you are compressing a gas, PV changing, T also will be changing, temperature changing. So, a very high amount of compression happening, that means very high temperature will be generated. So, if in one go if you want to compress, the temperature, the heat generation will reduce system performance. So, in that case you have to make interstage cooling system. Again, one cylinder is not used normally, there will be multi-cylinder system. So, multi-cylinder system with multiple intercooling system, it will create a efficient system. If you want to use centrifugal compressors, centrifugal compressor like centrifugal pump you have seen. So, similar way, centrifugal pump you are delivering liquid, but in this case you are delivering air or natural gas. So, natural gas you are compressing, again the same phenomena is there. When you are compressing at very high rate, high temperature will be there, then you have to dissipate heat and you have to compress it stage by stage, one by one, then you can get proper compression. Thank you very much.